We are very happy today that Nuh Gedik from MIT accepted our invitation to give a JQI seminar. He's working on exploring material with interesting optical and sometimes electrical techniques. I personally have been inspired by many of his works. JQI traditionally has been more AMO on the atomic side, manipulating atoms with photons. But in material, things get very, very complicated. And then making sense of things sometimes are very hard. And his group has managed to actually make sense of things that are very complicated. So I was very happy that he accepted our invitation to come and kind of bring the more condensed matter experimentalist viewpoint to the AMO. With that, I'll leave the.
Thank you. Good morning, everybody. So I should mention that it's my pleasure to be here. I'm looking forward to learning a lot from you guys. So what I'm going to do today, I'm going to be telling you about experiments that we have done in iron phosphor trisulfide, which is a layered antiferromagnet material. And what we did very briefly, this is a compensated antiferromagnet, meaning that it has no net magnetization. There is enough up spins, the same amount of down spins. The net magnetization is 0. And we ended up exciting this material with a high intensity terahertz pulse. And as a result, we saw that near the phase transition, magically, net magnetization popped out. So I will explain this a little better, but this is kind of the summary of my talk. But don't go to sleep yet. So before I actually show you what we did, let me acknowledge who did the work. So the most important people are those 3 people in my group. So my previous graduate student, Batır İlyas, and another graduate student, Michael Luo, in collaboration with a postdoc, Alex von Hogen, are the main heroes of this work. Batır is now a postdoctoral scholar at Berkeley, and Alex is on the faculty job market. And this would not have been possible if it wasn't a collaboration between the theory group of Angel Rubio, and Emil played a very important role here, as well as the materials we got from Jagun Park and his group members. And these are the agencies that gave us the money. So before I go into the details of what I did, let me actually zoom out a little bit and give you, in the way of motivation, why are we doing all this and what are we trying to learn at the end of the day? So as I mentioned, we actually realized a Terahertz-induced phase transition. But before I actually tell you the significance of this, let me actually remind you how we think about phase transition. First, in adiabatic, irregular phase transition that we realize with temperature. And then I'm going to talk about how do we do this with lasers and with terahertz later on. So when we think about regular adiabatic phase transitions, this is kind of the picture that we have in our minds. This is a free energy diagram. And at high temperature, you are here. And when you cool the system down, there are multiple minimas that exist in the phase transition, in the phase diagram. And what the system does, you give it enough time, it will figure out what is the lowest global minimum of the energy. And we call this a phase transition. And there's a phase right there. Now, we have known that you could actually do something similar with light pulses. You can come and excite at low temperature with an ultrafast laser pulse. And then what you do is you essentially go into something that's similar to a high temperature phase diagram. Doesn't have to be thermal. Sometimes laser excitation creates a different energy landscape. And then then this is happening all in ultrafast timescales. And this is something similar to a quench. Then the system comes back down, but then as it comes back down, because this happens very, very quickly, it can get trapped in one of these, not global, but a local minima, right? So what you ended up doing is you hit with the laser and you go into a phase at low temperature, let's say, that normally does not exist at in equilibrium. But if you give it enough time, the system relaxes back, right? So prototypical examples of this is that typically you excite with like a optical pulse, right? Has EV level of energy. And when you kick it with a material with this kind of a pulse, electrons are heated up, right? And then electrons heat up to 1,000 Kelvin or more, right? So it's rather violent, right? So even though the lattice heating is small, the electrons are really heated up to high temperatures, and then you can't really control where you go. So this works. There are very good examples of this, but there are challenges, and one of them is something that I just mentioned. You are rather exciting this in the electrons are driven to thousands of Kelvin, and then it also lives a short time, picoseconds at most, right? Maybe 10 picosecond on that order, right? If you want to do something with it, it's a little bit hard. So the question is, can we go around these challenges, right? I don't want to excite this, drastically. If possible, I don't even want to go to the excited energy service. I want to do everything in ground states, right? So the only reason why I'm going here because I can't really go over this barrier here. I will need to go up there and then come back down. This is much higher than KT, right? But is there a way, a clever way, that I can do all this manipulation in the ground state? I don't want to excite the electrons to thousands of kelvins. And if possible, I want to make this live longer. So it turns out that there are different approaches, and this can be done. But today, I'm just going to give you one example. And the example that I'm going to give you relies on already existing strong couplings in the material. So in solids, we have the structural degree of freedom, we have the magnetic degree of freedom, we have the electronic degree of freedom. And these three degrees of freedoms, they can be very strongly coupled to each other, right? Imagine that you have a solid in which the lattice is very strongly coupled to the magnetism, all right? Suppose I want to realize this magnetic phase transition. I am in equilibrium here, but I want to go to this local minima, but I don't really have a very good way of coupling to magnetism with light, right? Suppose I could actually couple to the lattice excitations, and what I could do is I can excite a phonon, right? Something like this. So I kick this phonon, and if I drive it to very high amplitudes, what I could do is I could use this coupling between magnetism and lattice, and I can realize this phase transition. Remember that my dream is to do this all in the ground state, right? I don't want to kick electrons very high temperatures. All I'm doing is I'm just driving this phonon, right? So what I'm actually describing to you is one class of light-induced phase transitions. This is usually known as like you are selectively driving a collective mode, and then the high amplitude of that collective mode is leading to a transition. And other people have done this before us. This is pioneered by Andrea Cavallari and his co-workers. But today I'm going to go show you one very recent example that we did in our lab. Okay, so with this intro, this is my outline. First, I want to introduce you to this material system that we studied, iron phosphor trisulfide. It's a layered antiferromagnet. I'm going to tell you what's interesting about this system. And then I will tell you about our experimental technique. We are exciting with a high intensity terahertz pulse, and we are probing it optically. And then at the end, I'm going to summarize and tell you what this all means, and then what we can do next. So let's begin with the material. The material is a member of this family, so some sort of a transition metal. It can be iron, nickel, or manganese. You have phosphor in here, and then you have either sulfur or selenium. And all these compounds, they are layered materials. The magnetism comes from this transition metal. So in the case of an iron, or in any one of these, it actually forms a hexagonal lattice like this. This is the first layer, this is the other layer. So it has monoclinic structure. It's displaced a little bit, the layer beneath it. And all the magnetism comes from these exchange interactions. So J1, J2, and J3. And depending on the values of these J1, J2, and J3, the system could be in different types of magnetic states. So for example, for the material that I'm going to be talking about, iron phosphor trisulfide, the values of J1, J2, J3 are such that the system realizes this is zigzag antiferromagnetic phase, which means that if you look at here, all the red iron atoms are spin up, all the blue ones are spin down. So these are ferromagnetically coupled along the chain, antiferromagnetically coupled between the chains. And if you look at the layer beneath that, it is antiferromagnetically coupled. So this was spin down, this is spin up now, etc. Right? So this is called the zigzag phase, but there's kind of different phases here. It could even be ferromagnetic. But one thing I want to point out is that this is kind of a theory diagram here. And what we are already seeing is that this iron phosphor trisulfide is kind of very near to the phase boundary, right? In other words, this is kind of very susceptible to a very small perturbation that I can make, either with light or something else, right? It can potentially push this system into, I don't know, the ferromagnetic side over here, right? So that's cool. Now, but there's actually something more important here that I want to show you about. So let's first, before we do anything fancy with, yes, please.
This is a phase diagram of a two-band like two-band spin model.
I believe so, yes.
And then experimentally, this is kind of people would.
No, this is all theory. Okay, so yes, this is so far all theory. Yes. So before I actually show you anything fancy, first what I want to show you is very simple characterization of this material. We're going to do Raman. When you do Raman, you can actually see a low energy mode, phonons on this material. And what you are looking at here is that this is the Raman spectra as a function of temperature. Here is the Néel temperature, something around 118 Kelvin is where this thing becomes this antiferromagnet. Whoops, what did I do? Oh. Oh, we are back.
It was you.
Okay.
Share this. I want to make sure we have the audio. Yeah. Okay.
All right.
Thank you.
Hopefully people in the Zoom can still hear me. So what I was explaining to you is before we do anything fancy, we just want to do a very simple characterization of this material. And we're going to do Raman spectroscopy. This is not my work, actually. This is from literature. People have done Raman on this. And what you're seeing here is that when this thing becomes an antiferromagnet, you could see that unit cell doubles, right? So this is up, down. And as a reason of this doubling, you can see that there are zone folding and new phonon modes appear. So phonon modes going up to, and then the unit cell doubles, and then the phonon mode zone fold. And this is what we are seeing below the AFM transition. We have new mode, right? Just from that level, the fact that magnetic doubling of the unit cell, zone fold, structural excitations already gives you an idea that there is very strong spin lattice coupling in this material, right? We'll actually see more evidence of this. So, and then what you see is that as a function of temperature, there's also this mode here that softens, right? This turns out to be a magnon. All the other ones are our phonon, but this one is a magnon. And in fact, if I just sit on this mode, okay, and if I put on a magnetic field, this magnon is doubly degenerate. And then you can Zeeman split this mode. It splits into up and top and bottom branches, right? So this is up to about 10 Tesla. But there's another work which actually pushed the. Right now, this thing doesn't work. Okay, perfect. So now up to 10 Tesla, you can see that this magnon mode is splitting. Nothing fancy here. Just a Zeeman splitting. But if you crank up the magnetic field even more, you see something very interesting. This lower branch of the magnon hybridizes with the phonon, and there is a beautiful anti-crossing between the magnon and the phonon. So yet this is another evidence that there is very strong spin lattice coupling in this material, right? And in fact, this is an inversion symmetric material. Magnetism doesn't break inversion here. And when you actually think about an inversion symmetric material, phonon modes are either Raman active or infrared active, but not both, right? You can either, so all these modes that we are looking here are Raman active phonon modes. But if you also do an infrared spectroscopy, you also see this mode here, this phonon mode with infrared spectroscopy. It shouldn't be there normally because that's not infrared active. But the reason why you are able to see it because it hybridizes with the magnon. So it has a little bit of a magnon character. And the reason why you can see it in the infrared spectroscopy is because this is magnetic dipole absorption. So in other words, you are exciting this phonon through the magnon, right? So those are very, very strongly coupled. So even in zero field, when you have zero magnetic field, the right way to think about this phonon is not just a phonon, but it has some character of the magnon as well, right? So I did all this to actually, yes, please.
So the Raman also shows the magnons?
Very good.
You said that there was a
very good question. Yes, indeed, those phonons also have some magnon character in them as well. Yes, yeah, yes. So now that we hopefully believe that there is a very strong coupling between magnetism and structure in this material, my next question is that could we now utilize this strong coupling, and could we do, what I just illustrated to you, somehow by exciting the lattice, which we know how to do, could we realize something in magnetism? And this brings me to my next section. So now I'm going to tell you how we actually did that. So the experiment conceptually is very simple. What we did is the following. As I said, we don't want to heat up the electrons to thousands of degrees, right? We want to avoid that. The band gap of this material is somewhere between 1 and 2 eV, something like 1.5, 1.8, whatever it is, right? Now, if you bring optical pulses, you can excite across the band gap. That's not what we want to do. Instead, we want to couple directly to the structural excitations. These phonons that I showed you, they are in the like MeV range, milli-electron volt range. So what we're going to do, we're going to bring this intense terahertz pulse with bandwidth that goes up to 25 MeV, far below the band gap of the material. It's not going to do anything to the electrons. And then this is going to be our excitation pulse. And then we want to monitor what happens to the magnetism. And the way we're going to do that, we're going to bring an optical pulse, okay, visible pulse, and we're going to look at what happens to the polarization state of this pulse, right? By actually measuring whether the polarization gets rotated or polarization becomes a little bit elliptical, we can learn about the magnetic state of this material.
Magnetic state meaning magnetization.
Magnetization, that's right. That's right. I mean, for that, you need a bit more modeling, indeed. So just a bit more precisely, we're going to measure two things. We're going to measure the polarization rotation. This is a linearly polarized light, and then we align the polarization somewhere between A and B axis. And by understanding how much the polarization rotates, we can actually know about the difference between index of refraction, the imaginary part of the refraction, and index of refraction between A and B. And by measuring the ellipticity change, we can measure about the real part. But I won't go into too much details. All right, so let me show you our excitation pulse. So this is the pulse. The way we create this pulse is we start with an optical pulse. We actually send it to a nonlinear crystal, organic crystal, and there's some sort of fancy, difference frequency generation inside the crystal. And as a result, what we get out is something like a pulse that has about 5 terahertz bandwidth. And you can picture this as a giant electric field oscillating up and down about terahertz frequencies. And if you do a Fourier transform of this pulse, you can easily see our frequency bandwidth here. And those lines that I'm showing you are from the Raman data. So these are the phonon modes. The red one is a magnon, and there is one here outside of our bandwidth, right? So I just want to show you that our pulse has nice bandwidth covering all these Raman modes, right? All right, so we're going to kick with this pulse, and then we're going to look at the ellipticity change of the optical pulse as a function of time delay between the terahertz pulse and the optical pulse. So we can change this time delay, and we can measure the state of the sample after any time. Yes, please.
Sorry, I have a question about the sort of setup here.
Sure.
Why does the complex part of the index of refraction not just correspond to absorption? Right, so normally I think about the real part is the phase delay. The complex part is, or the imaginary part is absorption. You're saying now it's more like the difference of the index of refraction for linear polarizations versus circular polarizations.
I didn't quite say that, but you're right. The imaginary part, this is, so all I'm saying is that, this is A and B axis, right? We send a linearly polarized light this way. And then when this pulse goes through, two things can happen to this polarization. It can rotate, or it can get some ellipticity, right? Now, if you work out the details, if it just rotates, that actually tells you about, so here, if it just rotates, polarization rotation is related to the difference between the imaginary part of the A and B. I mean, you can kind of picture this, if this is A and B, and then you send this, if you decompose it into two axes, imagine that this becomes a little bit smaller, right? if the b-axis absorbs a little bit, as you said, it becomes a bit smaller, then the whole thing is just going to rotate, right?
I see.
Yes.
So this isn't a Faraday, like a Faraday rotation.
It's not.
Okay.
It's not. So I will get back to there. Yes. Very good. Okay, going back to the experiment, this is the pump excitation pulse. And now let me show you the signal. So when we probe it with this optical pulse. So this is just an example spectra at 10 Kelvin. What I'm plotting is the ellipticity change of this pulse as a function of time. We see a very similar thing in the polarization rotation, but I won't show you for the sake of simplicity. And then the x-axis is the time between these two pulses, which I can change. I can send it either before the terahertz pulse, which I see 0, which makes sense. This is the equilibrium state. There's no change in ellipticity. Or I can measure it during the pulse. You can see that the pulse lasts about 1 or 2 picoseconds. You can see that there's some bigger signal here. And then after the pulse is gone, there are ringings that I see. There's clearly multiple modes that last for a long time, right? So for one thing, you know, the signal right within the pulse, we know this is coming from, you know, optical Kerr effect, which is that, you know, when the light is incident on the sample, it actually changes the optical properties. This is the terahertz Kerr effect. So for the purposes of this talk, I'm just going to ignore this. I will only concentrate what happens after the light is gone, right? All right, so now it's a bit hard to look at the time domain, but what I could do is I can just take a Fourier transform of this part, right? So when I did that, here is what the spectra looks like. So again, this yellow thing is the bandwidth of our pulse. And these oscillations, they correspond to very nicely to these modes, Raman active modes that we have in the pulse, right? So these two are mainly phonons. This is a magnon. This is another phonon. What's amazing is that we have one here. The strongest one is actually outside of our bandwidth. And the reason that is this is a Raman active mode, right? Which means that you cannot directly excite it with infrared active right processes. So it makes sense that it's outside of our bandwidth, but you could do a 2 photon, right? You can 2 terahertz photons. This is an intense pulse can come together and excite that one, right? So this one is a magnon here. And now then the next question is, these are Raman active modes, right? I'm not exciting this mode just by absorbing a photon at this frequency. How am I exciting them? So to understand how, yes, please.
You're going to go back to that peak because naively I would have thought that that peak would be weaker than the original ones. Because you're exciting
that's right.
that is nonlinear. Right?
That's true. But I won't go back to this peak, but I'm going to show you that even these are excited nonlinearly, right? So these are all Raman phonons, right? Raman active phonons. So how am I exciting them? So let's start with the magnon. That's the easiest, right? Magnon has magnetic dipole absorption. If I plot the amplitude, this amplitude of this magnon as a function of the electric field of the terahertz pulse, you can see a beautiful linear curve. That makes sense. It's magnetic dipole absorption, right? Now let's look at this phonon here, the one that's actually a little bit farther than the magnon. This phonon has a beautiful quadratic dependence. That also makes sense. It's a Raman active phonon. So I'm not exciting it directly with just absorbing 1 photon. I need 2 photons, right? You could do a process like this, you know, up and down, come back to this, or you could have a 2 photon absorption, some sort of a 2 photon process, right? Now, if you look at this one right here, which is closest to the magnon, you see something funny. It has both a linear character as well as some minus something quadratic. It's not a saturation thing, actually. We can make it go the other way as well. So it's a combination of a linear and a quadratic term, right? So if I actually summarize, the magnon is excited with magnetic dipole absorption. The Raman active mode here, the phonon mode, is with 2 photons. And this guy right here is actually some interference of both a Raman active process as well as a magnetic dipole absorption. So both of them are there. I won't talk about this, but if you look at it, it's purely quadratic, right? So somehow the matrix element for that phonon is the biggest, right? Very good. So now that we know what we are exciting and how we are exciting, now I want to show you what's interesting, okay? So far I only show you data at 10 Kelvin, right? We cool down to the lowest temperature and then we just measure this. We see all these excitations. Yes, please.
Yeah, so you have the phonons and magnons, but it's not clear to me like how big the spot size is. do you have dynamics going back and forth between the two interfaces of your crystal, or
sorry, I should have made the geometry a bit clear. So this is excitation with the terahertz pulse, right? The pulse, 1 terahertz wavelength is about 300 micron. So the lowest I can focus is something on the order of a millimeter, right? So my pump pulse is like big, it's like millimeter. And my crystal is, something like, I don't know, 50 to 100 micron thick. It's like a bulk crystal. And then my optical pulse is, something smaller than the pump. I'm coming and probing I hope I answered your question. Good. So now what I want to show you is the temperature dependence. This is at low temperature, but what happens as a function of temperature? So what we find is that something very interesting happens as a function of temperature. And first, I just want to show you raw data. So here again, this data that I showed you, 10 Kelvin data, right? Now we're going to warm up the temperature. The Néel temperature is right here, 118 Kelvin. And when you go above Néel temperature, you lose most of these phonons. Some still remain. Kind of makes sense with the Raman, right? So these modes were zone folded, but when you go about, you lose most of them, but not all of them. So you still have, a ringing phonon here, but most of them are gone, right? So it's easier to look at in the, maybe some of you can take the Fourier transform in their heads, but I cannot. So if I look at the Fourier transform of this data, so first we see at 10 Kelvin, these are beautiful modes there, right? At around the Néel temperature here, we also see that we lose most of them, but some of them still remain there. You beautifully see that this magnon is softening. It's also seen in the Raman data. So all of that is nice, but we already knew this, most of it. There's one thing that's actually not expected. So, and that is, there's this intensity right here. Around T Néel, there's something that's showing up around, I don't know, DC, right? So what is that? Now, you can always be fooled by the Fourier transform. So the best thing to do is always look at the raw time traces, right? Let's look at what's happening around T Néel. So if I look around T Néel, this is the curve that's closest to T Néel. What you can see is that I start from 0, I do something, it oscillates, but it never comes back down. As opposed to, if you look at all the other temperatures, right, 10 Kelvin, things oscillate around 0, right? Again, it's a 50 Kelvin or above, but right around T Néel, I get this offset. So first I saw this, I said, well, I mean, you're only looking at 15 picosecond, right? If you just go a bit longer, it's just going to come down. It has to come down, right? So what we did is then we increase this time 10 times, right? Instead of 15, go to 200, right? And that's this data right here. So this is around T Néel again. And then we see the ellipticity change. This is a bit coarser. That's why you don't see the fine oscillations. But the point is that this thing is still there. There is no intention of coming back down, right? So there's some very long-lived thing. So this is 200 picosecond by now. So at this point, I don't even know when this is going to come down, but I'll show you. We have a way of measuring, right? So just to actually tell you, our laser has a repetition rate of 1 kilohertz. So there's the time between the two pulses is 1 millisecond, right? So we are still looking at only, the 200 femtosecond, but technically this time delay here is negative time delay is like 1 millisecond time delay because the other pulse arrived 1 millisecond before this. Okay, so if I now sit here at this time delay, and if I understand how does this thing depend on temperature, if I plot that temperature dependence, we see a beautiful divergence here, right? So this is the T Néel, and this is the temperature difference between T Néel and the temperature. You can see that this thing, both below and above, diverges, right? Somehow you can actually fit this thing with a power law, and I will show you later on. Okay. So what's going on? So coming back down to what exactly are we measuring? We are measuring in this particular experiment ellipticity change. And it can come from two things. It can either come from linear birefringence, going back to this, we have A and B axes. Suppose the absorption is not different. All we are changing is just that we are getting a bit of a phase in this direction. So if you get a bit of a phase here, obviously we will acquire a bit more circular polarization, right? And that's one possibility. The other possibility, though, it can also come from circular dichroism, right? Normally, circular dichroism you see in things that are magnetic, or sometimes you can see it in chiral things. But we checked, this material is not magnetic, we know that, but just to be sure, we actually did a static circular dichroism study. We looked for circular dichroism in this material, and there is no circular dichroism in static, right? But the question is it possible that after we kick with the terahertz, this is becoming magnetic, and we are getting some circular dichroism? But this is an experiment that we could do, and we can check. And how do we do this? We do it in the following way. So this time, we change our probe, and we look for first with a right circularly polarized pulse, and then with a left circularly polarized pulse. If the transmission is different after we kick it with the light, then there must be some terahertz-induced circular polarization. Indeed, so one of them is right circular, the other one is left circular. And you can see that very nicely, after you excite with the terahertz, there's a big difference. In fact, if I take this difference, and this is the difference between the two circular polarizations, and if I plot it, the temperature dependence on the same axis as ellipticity, you see that this ellipticity is mainly coming from the circular dichroism. So what this experiment is saying, something very clear. You kick with the terahertz, then you get circular dichroism. It must be that the sample is becoming magnetic. It's very weird. How so? I mean, how is it possible that it becomes magnetic? In fact, you can fit it here with a power law, and you get some critical exponent, and it turns out that this is the same exponent you would expect if you have a 3D Ising system. And this material, the spins are all out of plane. They go up and down. It's very close to 3D Ising, so we are basically seeing that as well. Now, another thing that's interesting is I can look at the time dynamics. So if I look at first this rise time, the rise time is also becoming very, very slow. And around the Néel, the rise time also diverges, right? It goes up to 30 picoseconds. And this also can be fit with a power law as well. Now, coming back to the decay time, from here, I cannot measure it. It's just too long within this time scale. But I can do a trick. The way I'm going to look at it is I'm going to look at the negative time delay, knowing that that's a 1 millisecond. First thing I can do is I can very, very, fine temperature steps approach to Néel, right? So here's 115 Kelvin. And as I'm approaching the Néel, this 1 millisecond time delay, the negative time delay, you can see that as you get closer and closer and closer to the Néel, even after 1 millisecond, the signal doesn't die, right? So that's because it's actually diverging. The decay time is diverging around Néel. It turns out that it's about 2 milliseconds. So we can actually do some tricks. We can, instead of sending pulses at every millisecond, we send the pump pulse every 2 milliseconds, but the probe we can measure at every millisecond or every 3, every 5. And that way we can measure very nicely what the decay is. It turns out about 2 milliseconds is the highest.
Your terahertz pulse is linearly polarized.
Yes.
What breaks the symmetry?
Very good question. Very good question. I will explain in a second. It's some coupling within the material. Okay. So in other words, I'm going to go ahead a little bit myself. What we believe is happening, we are driving a specific phonon mode, okay, non-linearly, okay, meaning that the phonon mode normally goes up and down, up and down, up and down like this. But if you excited with like a linear electric field, suppose it goes with E squared, okay, then you have a net displacement, right, of the phonon mode. Now, the coupling constant in front of that term is what breaks the symmetry. It always goes one way. But I'm going to explain it a bit more. Yeah. Question? Okay, good. So, very good. So, it is a long-lived signal. It lives about 2 milliseconds. All right. So, now just to summarize, after terahertz excitation, we get net magnetization. The amplitude of this thing diverges at Néel, and the rise time diverges at Néel, decay time diverges at Néel. The observations are clear, but I absolutely told nothing about why this happens. So that's my goal now, is to explain how is it that this happens. So how does this work? So we looked first into the literature to see different ways that this can happen. And we found there's one very nice experiment done by Andrea Cavalieri and Ankit Tissa. And what they did is they did a similar experiment on a different antiferromagnet, cobalt ferrite. All right. In this system, there's something called a piezo-magnetism, meaning that, imagine that you have an antiferromagnet. Normally, that's fully compensating. But then in some materials, if you apply strain to this system, And then if you go one way, what you do is you change the crystal field splitting, and then you change the local magnetic moments. All right. So in equilibrium, this was fully compensated. Up and down, they were canceling. But then if you go one way, you have one magnetization. If you go the other way, you have another magnetization. And what these guys have done is they kind of realized a version of this with light. So somehow you excited the light excitation by pumping with the terahertz. It just does exactly the same thing as what a strain does, right? So this is called piezo-magnetism. Now, for this thing to be allowed, though, what you need is that you need to get a net magnetization on the left. You need to apply strain, and the material must be breaking time reversal, because if I flip time reversal, this flips sign. Strain doesn't do anything, so this must be flipping sign. So what you understand from this is that piezo-magnetism is allowed in materials that break time reversal symmetry. Well, you might say antiferromagnets are going to break time reversal symmetry, but not necessarily the case. In some antiferromagnets, if you simply just flip the spins, if you just change time reversal, you just flip the spins, right? But then a simple translation brings you back, right? So flipping the spins and a simple translation by a lattice constant gets you back, right? But in some antiferromagnets, you cannot do that. So it turns out that cobalt ferrite is an antiferromagnet that breaks time reversal, so this effect is allowed. But this is not allowed in iron phosphor sulfide. So this is a nice mechanism, but doesn't explain our effect. Okay, so then what happens? So then the question is this. I'm driving this with a very strong field. I'm exciting all these phonon modes. But then you can ask, is it the field itself, the strong field itself, or is it these modes that I'm driving that is inducing this phase transition, right? Is it the field or is it the modes? But this question is a question that can be addressed, right? This is the experiment that I already did, right? So I drive this thing with a strong field that has bandwidth that covers all these modes. I get this long-lived signal. But what I can do, I can generate another terahertz with a different mechanism that won't cover these modes, like this. This is actually in collaboration with Keith Nelson. He has this other terahertz source that has even higher field, but doesn't cover these modes. When we do our experiment with this terahertz source, this whole thing goes away, right? So this is a very clear answer. It's not the field. It is the modes that we are driving with the field that actually gives rise to this phase transition. Okay, well, that's good. But how? How is it that these phonon modes, when they are driven to high amplitudes, give rise to a net magnetization? So to understand this, what we did is we collaborated with our theory colleagues. Angel Rubio and Néel was the people who played the key role here. So first, what they did is they looked at these phonon modes. So this is the phonon modes that are that I was showing you within our bandwidth. So these three of them. This is the one that's close to the magnon. This is the one below. This is the one above. So first, it actually is very pedagogical to look at what they look like. So if I just freeze them in time, this one is like an out of plane symmetric mode. One goes up, one goes down. This one is an anti-symmetric mode. You can see that this one doesn't really affect the bond length. This one makes this bond length longer, this bond length shorter. And there's this symmetric mode that changes them symmetrically, right? So this is symmetric, this is anti-symmetric. Now, first thing that they did some spin Monte Carlo. And just by looking at the thing, they looked for some magnetization that's coming out. They found that only in this mode, you actually get a magnetic state. And the reason is very easy to understand after you know it. So when you modify these bond lengths, what you're going to do, you're going to change the exchange interaction. So when you make this bond longer, the interaction between these two spins are going to be less strong. When you make them shorter, it's going to be stronger. So you can actually calculate how does these J's, the exchange interactions, depend on the specific phonon, right? Now, it turns out that if you have this phonon mode, this can give you net magnetization. So I'm going to explain it how, but before I even explain it to you, I just want to give you an intuitive picture. So before we had two chains, right? One up, one down, and they were exactly the same. They were canceling each other. But now you weaken the exchange interaction on the top one, so the spins becomes more floppy. So compared to the bottom one, which is enhanced, right? So the net magnetization on this chain is going to be less. This chain is going to be more. So you get net magnetization, right? But let's actually make this a bit more precise. So now, if you focus on this phonon mode, what I can basically do, first, this is the Hamiltonian, right? Just the regular parts, kinetic energy, potential energy, and the magnetic part, right? The coupling between the spins and the anisotropy. But then once you have this phonon mode, you change the J's. So as a result, you have another term in the Hamiltonian. This another term is going to look like this. So now, if these are the spins, S1, S2, S3, S4, I have a little bit of less J here. So S2, S3 will have different sign compared to S1, S4, right? So then you can see that this is going to be the net change in the Hamiltonian. Now, if you express this term in terms of the antiferromagnetic order parameter, which is kind of the sum of these minus the sum of these, and the ferromagnetic order parameter, which is the sum of all these different spins, you can actually rewrite this term as simply coupling between L and M. Okay, so L is the antiferromagnetic order parameter, M is the ferromagnetic order parameter, and then Q gets in there because the phonon is the one that actually determines how this thing happens. And this term is now the only extra term that you get. So now that you have this very nice coupling between the two, you can rewrite the free energy. And what ends up happening is that now what I need to do, I need to include this coupling between the two orders, right? So some coupling constant, G, L, M, Q, I said, and then now there's this coupling between L and M. Now, if you solve for this free energy, what you find is the following. So the true minimum of this free energy is no longer at, M equals to 0, right? It turns out that you can even minimize the free energy further at a finite Q and a finite M. So the system actually prefers that this phonon mode is displaced a little bit and you have a net magnetization, but it can go both ways. There's a minimum at plus Q and plus M and minus Q and minus M as well, right? So before we derive the system, in equilibrium, the system already has these minimas, but we do not see any net magnetization in equilibrium, right? What must be happening is that these minimas are very shallow. So the system never orders, right? So they're kind of always in superposition between these two minimas. But then what you do is you kick with the terahertz pulse, you drive these phonons non-linearly. It's important that you're not driving them linearly, meaning the phonon is not just going up and down and the net displacement averaging out to 0. We are driving them non-linearly, meaning that something like you drive it with E squared rather than E. So there's a net displacement in one direction set by the material properties, right? So as you drive this phonon only in one direction, you actually you pick one of these minimas, right? So let's say you only drive it in the plus Q direction. The system gravitates towards this minima. And then, if you wait long enough, the system relaxes back to its original state. Now, the reason why this is slow is actually the movement in this free energy diagram around T Néel. It's set by antiferromagnetic fluctuations, which actually diverge, right? I mean, when you get very, very close to this phase transition, the time scale also diverges. So if you actually minimize this free energy, and if you look for the equilibrium magnetization, it goes like L square, which is proportional to the fluctuation, not the L itself, but more its fluctuation. And this is expected to diverge, and that's why we were seeing the power law type of scaling. And this is also a nice way to understand why the time scale diverges, because the fluctuations also diverge in time as well. So let me summarize what I told you so far. We have done this experiment where we excited this layered antiferromagnet with a terahertz pulse. We have seen these beautiful Raman active phonon modes and the magnon. And we also saw that right around T Néel, there's net magnetization in this material. And we understood it basically by this nonlinear excitation of this phonon mode, which couples antiferromagnetic and magnetic order parameters. And then as a result, you get a state that you don't have in equilibrium. Yes, please.
Yes, so the previous slide maybe.
Yes.
So if I understand correctly, depending whether you drive phonon non-linearly,
yes,
the positive or
that's
negative, right, you're going to get positive or negative magnetization.
Not what you are saying is correct, but whether or not you get Q or minus Q, we cannot control.
Yeah, that's what.
Yes, that's right. We cannot, because there is a term in the system So this can happen in different ways. One way it can happen directly, the electric field E squared can be deriving. So this is just a Raman process. That's one way. The other way, actually, a Raman, an infrared active phonon mode can be coupling to the Raman active phonon mode. So it's like Q squared Q. Instead of E squared Q, there's a Q squared Q. But in all those cases, these terms in energy has a coefficient in front, and that coefficient is a material dependent coefficient. It's not something that, or in other words, I cannot flip the phase of my terahertz. It doesn't flip the sign of
material. But
exactly. That's right. Exactly. That's right. Yes.
But sorry.
Yes.
Then, if it's not magnetic origin, if that term doesn't
Yes.
break time reversal symmetry, I do an experiment once, I should get M plus M. I do an experiment another time, I may get minus M.
No, because the sign of that term is always fixed by the material. You don't get the another term.
Functional symmetry. See, once you get magnetization, that breaks time reversal.
Right.
Right? So, and then either your crystal intrinsically breaks time reversal, or your optical pump somehow is non-time reversal symmetric. If your optical pump is time reversal symmetric, right?
Yes.
Then the output, magnetization positive or negative, that breaks time reversal symmetry. And you say it breaks consistently, not randomly, but repeatedly.
That's right.
So that means somewhere there must be something.
Well, that's the sign of that term in the Hamiltonian. That's what it
has antiferromagnetism.
Yes, possible.
And the antiferromagnet translates something
actually, yeah,
into this.
Right. That's right.
Is there like a mirror symmetric crystal structure that would give you the opposite sign?
What your confusion was that you showed Andrea's paper.
Yes.
Yes. On kids. So there they had some magnetization. So that lambda had broken time reversal symmetry.
Right.
If this material does not have that coefficient that breaks time reversal symmetry, then every shot I do the experiment, I should get one sign of the magnetism.
So maybe I can reinterpret your question this way. So this is actually what puzzled us a little bit. So this was So what one thing that puzzled me is that this thing, L, the antiferromagnetic order parameter, it should have domains, right? Because sometimes it will be this way, sometimes it will be this way. So what I was expecting as a result of this experiment is that, if I have this domain, then maybe I see one sign. If I have this domain of L, I see the other sign. So this is something that really puzzled me, right? But then I understood, not me, but the theory colleagues helped us to understand it. And then the way we understand it is the following. So it turns out that this particular phonon mode that we are deriving is a Raman active mode, which means that it should be inversion symmetric. So meaning that if it is displaced one way in one layer, in the other layer it goes the other way. Okay, so it's because these layers are antiferromagnetically coupled, it turns out that different domains of L is really essentially translating the sample by one layer. Okay, so yes, indeed, when L changes sign, Q also changes sign. It has to, okay, because it's a Raman. So because L times Q appears the same in the term, right? In different domains, the magnetization does not change sign. It always points the same direction. I don't know this answered your question, the original question, but this is one thing that we struggled with in terms of the domains. Yes. Yes, please.
I guess maybe a variation of the question.
Yes.
Is that your circular dichroism system, it's a signal.
Yes.
Broke a symmetry.
Yes.
That was originally unbroken.
That's right.
Right. So then the question is, so you always see the circular dichroism go the same way.
That's right. Yes.
But your signal, at least, is not apparent that your terahertz broke that symmetry.
That's right. The coupling of the terahertz to this term in the Hamiltonian that exists in the Hamiltonian, but can only be realized after you pump it, right? So there's a term in the Hamiltonian that goes like some G times Q infrared active phonon squared times Q Raman, okay? So that term can only be realized when you excite with the terahertz, and that has a particular sign in that term. That's what breaks the symmetry. It goes up or down according to the sign of that term.
That's a spontaneous breaking. Exactly. So that hidden magnetization. So imagine that there is some hidden magnetization. I can only see it this way.
Yes.
That there is some hidden magnetization. The expectation value of that is non-zero. But in the usual circle of diaphorism, it doesn't show up.
Yes.
And now with this terahertz, it becomes active.
That's right.
But that guy should have magnetic origin.
I mean, essentially, this is this, right? I mean, I do.
Meaning that expectation value
should be non-zero.
Zero.
I see. Yeah. Okay, interesting. Yes. Yes.
Another variation of this.
Yes.
Suppose you
good. All right.
Yes. Understand what's perpendicular to the sample.
Yes. Yes. Yes.
So you send your light and you see no circle that rate. Okay.
That's right. Yes.
You magically preserve this and flip the sample. From this point,
yes.
in opposite direction.
That's right.
Then you will see the opposite diaphragm.
Well, I'm not sure. It's possible. Okay. I haven't done the experiment. Okay. So no. The only reason I'm not sure, this is a very good point, and we thought about it, we didn't do the experiment. The only thing that I don't know is when you flip the sample, right? And when you send the terahertz the same way, will Q, the phonon, flip or not? Right? I have to think about that. So if the phonon doesn't flip, you're right. The magnetization should flip. But if the phonon flips, then I'm not sure.
At least experimental.
Yeah. So we can do that. Yes. Yes.
We have lunch too.
Okay. Sorry. Very good. Yes. Yes. Okay. So how am I doing with time? So I should wrap up, right?
Yeah. But
yes. Yeah. I mean, what's vision afterwards? All right. So very good. Okay. So what I told you so far is, remember, I started with a broad picture, meaning that there are these local minimas in the thing. I didn't want to go to the excited state. What I did is I did some manipulation in the ground state with this terahertz pulse. We ended up with another local minima, but we still relied on the existence of another local minima. In equilibrium, there was something, right? It wasn't just realizable in equilibrium, but we did it. But imagine that I want to actually so this is what we did, right? So there was an existing minima, and we went over this, etc. But imagine that I want to do this without this existence of this local minima. Could I just take any system without having a local minima? Can I engineer something with light? All right. So that's the next question. That's the next level. So I want to cut it short, but I just want to show you what I'm thinking about. I believe this is possible. And the way this can be done is something that we have done about 10, 15 years ago. We basically, in AMO, maybe you are very familiar with the Floquet states, but in condensed matter, this was a very important question, whether you can see Floquet-Bloch states. In other words, if you bring light that's less than the band gap of the material, will you realize a regime where the electrons will realize the periodic modulation with light, and then you can dress the band structure? Indeed, this is what it is. You know, you have these states that are h bar omega separated. But the important thing is that, you know, these states, you know, when they cross, for example, you see anti-crossing gaps. So for all practical purposes, these Floquet-Bloch states is a way of engineering the band structure, right? So my vision or dream, we're not there, is whether you could use approaches like this to engineer band structures on demand to realize phase transitions without relying on an existing minima, right? So just I want to conclude with one example. This is from our original work, where we were looking at a topological insulator. Without the light, you see this very nice Dirac spectrum. Now, if I look at the point here, this is protected by time reversal symmetry, right? Now, if I take a cut across this point, you know, before the light, you see just the Dirac point here. Now, if you drive it with linearly polarized light and take the same cut, this is the red points here. You don't do anything to this point because it's protected by time reversal symmetry. But if you drive with circularly polarized light, even by eye, you can see that there's a gap that opens up here. And if you look here, there's indeed a gap that opens up. So just by driving this thing with circularly polarized light, you break a symmetry, you open up a gap, and this phase that you realize is actually the Haldane phase. Mathematically, it's the same thing, right? In fact, later on, you know, my previous student, James McIver, went and worked with Andrea Cavalieri. They did exactly the same phase in graphene, and they were able to measure a sigma xy, right? Showing that it really indeed exists there. Anyway, so We did the same thing in TMDs. We were able to drive with circularly polarized light detuned from the band gap. And then we were able to shift the values one way or the other, depending on which one we drive it. So the bottom line is this, that, and we recently saw the same effect on graphene, that these Floquet-Bloch states, they are both our group and other group, that they showed it simultaneously. So many other phases you can potentially realize with these approaches. Now, we are not there yet because this is a kind of a younger field. It's a little bit harder to do, but my hope is that by using approaches like this, you don't necessarily need to rely on an existing minima. You could actually potentially engineer phases on demand. So with this, I want to thank you with your attention, and then I'm going to leave you. I'll just skip this with the picture of my group. Thank you. Yes, please.
So I was curious about the flexible, or how much degrees of freedom you have with the terahertz.
Yes.
Like, so in theory, I can imagine that I can shape it arbitrarily and send just some profile.
Sure.
And then hope to get some kind of crazy nonlinear dynamics of the ions.
Yes.
Is that a level of control?
That's a very good question. We are working on it. So if I understand your question, like would you be able to filter the terahertz pulse and a specific frequency? I don't know, only excite a certain phonon mode, for example. Is that what you're imagining? More. Okay. It's good to be a theorist, you know. I can imagine.
So I excite certain phonon mode with some amplitude and phase, another one with another amplitude and phase, and maybe some particular phase shifter, to be careful how you define. But if it's nonlinear, I can imagine like maybe, I don't know, the cube of the third multiple of one frequency maybe is close to the other phonon. Or so on.
I'll tell you another experiment which is related, not exactly the same, that we actually are doing at the moment, right? And that is the following. So right now I do know that I'm exciting this phonon mode nonlinearly. What I'm guessing is that I am exciting an IR active mode that nonlinearly couples to this Raman mode. But I absolutely have no idea which IR active mode that I'm exciting, because all I do is I kick and I measure, right? So the experiment that we are doing is the following. So we send 2 terahertz pulses, and then we change the time in between these 2 pulses, right? This is called 2D terahertz spectroscopy. And then a third optical pulse comes and probes the phonon. So what I can do, I was just showing you a Fourier transform, right, as a function of time. Now I can actually take another Fourier transform between these 2 terahertz pulses. So what this experiment allows me, it actually allows me to separate excitation and probe frequencies. I can see things like, oh, I can excite this IR mode and then this Raman mode rings, right? So this gives me additional degree of. So in principle, the experiment that you are describing is possible, because if you can shape the terahertz pulse, you can take 2 and then shape them differently. And then in practice, it's a bit more difficult, but it's a little bit easier the way I'm describing it. Yeah.
So maybe basic questions. Are these terahertz pulses coherent, or is it more like an intensity? Like, is it more like a laser, or is it more like
it's coherent.
It's coherent.
Yes. Are you talking about the 2 different ones, or the terahertz pulse within itself?
Within itself.
I mean, it interferes. We see interference. Yeah.
So you have really long times in there.
Yes.
And you were talking about critical exponents
Yes.
and stuff.
Yes.
Things diverge
Sure.
at these temperatures.
Yes.
The critical temperatures. So I was wondering, do you have some idea of what that time corresponds to, or do you have a time, like a thermal time, that you go back to the original well or something like that?
Yeah, it's a good question. I do understand what you mean, but I really don't have a good way of, guessing. You're saying that, would that time gives me some energy scales about, for example, right? Yeah, that's right. That's right. That's right. Yes, I do. Yeah, it must be corresponding to something like this, but I don't really have a good intuitive picture of how to describe it. All I know is that 2 milliseconds in my standards, like infinity. I mean, it's like very long. Yeah.
Yeah, it's metastable.
Yes.
I'm curious if you have done any experiment looking at the spatial dependence of the MCV.
Right.
So if it lives for 1 millisecond, maybe the magnetization can propagate over the entire sample, or you don't have the.
That's a good question. We haven't done any spatial dependence. We are kind of setting up something to be able to do that now. But another thing that we are thinking about is, if it really lives 2 milliseconds, we should be able to do transport right? That's what we're going to try, right? Kick it with then, just do regular transport, look for sigma xy or other things, Yeah.
So as usual, we have 4 p.m. Discussion for students with the speaker. Just a reminder. Thank you again. It was
Thank you.
very exciting.
Thank you.